Making a video. It's 5:30 in the morning. Why not? I haven't been to bed yet. Back. Bad. Anyway, Bill Gaede. I figure I'd do a video. He's been bitching about other people lately. Which is what I do. What is this stupid chat thing? Let's see what channel. It's got this on the DraftScience channel, but anyway. Sorry. So, he constantly makes this argument, which he won't respond to anybody else on Earth, so, which is just, so irritating. But he keeps making this argument that a particle theory can't do this and it can't do that. And yes, it can with a tiny bit of imagination. And so he's using Sean Carroll as an example when Sean Carroll talks about fields. But he's not talking about fields the way Bill Gaede wants to turn it into. He talks about fields in the sense that he says there's a force being applied to every location in space. And you could think about it that way. You could just say, what if I could put in, an immaterial element that could be influenced by the force in every location? There would be a certain movement in some direction from every location being implied by this force. Now, I would argue that you can fix all of this by recognizing that the forces extend beyond the electromagnetic spectrum. So, there was a period in history where, before Hertz, where Maxwell had sort of said, okay, we can expect there to be stuff. We had light, figured out as a frequency. And the argument was that, well, this other stuff, this magnetic stuff, the rest of it moves the same speed as light. So there was this obvious implication that the two frequency ends might have radiation. So there was this argument that there would be radio waves, the prediction, a pretty sensible prediction. And then 7 years later, Hertz figured out how to create a tuner and receive radio waves. Yeah, it still required a crystal, so you needed something to vibrate at the same frequency as you need something to sympathetically vibrate to create the electric current, to create the to receive the radio. And that's what they first used, was little tiny pieces of crystal. Because when they bend, when they move, when they vibrate, they create electricity. Or they allow a current to pass through more easily. They really were inventing the transistor, they just didn't know it. Also, but anyway, so physics figured that out. Oh, there's a whole spectrum. Now, what they haven't figured out, which is kind of obvious, and what Newton, he's bringing up Newton here, and Newton had this point made to him by Fabio, who 350 years ago explained that you could have an external pressure that's pushing everything together. And they discounted it because of one reason, drag. Essentially one reason. And they also thought it would create heat because they were thinking about particles like meteors hitting the moon. They weren't thinking of it kinetically. But if you make it kinetic, that is, all the energy stays in the particles. Photons don't lose any energy. You can only trap them. You can only catch them. And then they still have their energy. They're just not going anywhere. So they still have their forward momentum, the one you trapped, and everything else they do inside. See, if you trap something that's bouncing back and forth, the only momentum you trap, really, the only momentum you're catching is their initial momentum going this way. That's the extra bit. The back and forth will all erase over time. And so all you're left with, so you could hold it for 10,000 years, and all you really got was the little boost this way. All of this will mean nothing. Even if it's a circle, it would mean nothing. And the only thing that mattered was the first shot in. That's the way it works. So by creating these traps, you can disengage the field, force, the energy. You can make it inert while it's inside of the matter, except for the initial momentum. So anyway, Fabio explained this 350 years ago. Physics ignored it. Then, when they had the chance to say, well, maybe this electrical spectrum thing, okay, maybe this has to do with frequency. Well, what if this stuff doesn't have a frequency? What if you have the same stuff but no frequency? That would explain magnetism. That would explain gravity. Now, clearly, you have to come up with a more elaborate mechanism. So in the case of gravity, you have to explain drag, which means you just have to understand this trap thing, because then you can get rid of the drag by creating a little engine. And then in magnetism, this pressure works both ways. It works as repulsion or attraction. So you have to be a little bit clever and come up with the idea that maybe the force has two forces. Just like the magnet has two poles, the force comes in two varieties. So this is essentially what my contribution to mankind. It's also being ignored, but it's, in my opinion, and it's just no reasonable person who actually pays any attention to what I've been saying for 7 years, in my opinion, could say this isn't the right answer. You have to be unreasonable, plainly. Because it answers all the questions. It solves all these riddles. And it certainly explains how a particle force, a force that only applies positive energy, could create both attraction and repulsion. So it's really annoying that Bill Gaede says this crap and doesn't allow anyone. He is just as useless as the people he's critiquing, in the sense he's just as distant and just as disconnected from any real conversation about his physics. So unless somebody is being, what are you talking about, Bill? Asking questions like, what do you mean ropes? Or, something like that. He's not interested. So I don't know when he'll start getting onto ropes. I didn't watch this whole video yet. It's just that he does this routinely, this part. So I just wanted to make sure that, I just wanted to point out this part and explain that he's misparaphrasing conventional arguments by simplifying them way too simple. I mean, he doesn't really understand what they mean by field theories.
Puzzled by action at a distance. The Earth exerts a force on the Moon. They're not touching each other. The Earth seems to push out across empty space to exert this force.
Right. So that's sort of a primitive view, right? And I'm just saying, Fabio, 350 years ago, already pointed out that you can think of it a different way. You don't have to think about the Earth pulling the Moon. You can think about the fact that there's a background radiation of force that's pushing things together, not pulling them together.
Force. Newton said that this phenomenon of action at a distance made no sense, even though it was part of his theory.
Okay, it wasn't part of his theory. That's why he said it made no sense, all right? There wasn't any part of his theory that said any. See, these are little nasty misparaphrase. They're just unfair. Newton just made it clear. He tells you how it works. What it does. He doesn't tell you how it does what it does. And he made that explicitly clear, so there's no confusion. Newton didn't make any errors. He did really good work. And it's just bullshit to imply that somewhere in his theory is pull, because it isn't there. He didn't say how it happens. He says what happens.
How's it going to make sense if Newton cannot imagine a mechanism?
He could imagine mechanisms. He couldn't imagine one that worked, okay? Because it is a little bit complicated. Again, there are liabilities. Again, he was presented Fabio's theory. He liked it. So for a number of years, he communicated with Fabio. So, and then he, for whatever reasons, decided it's not good enough. Or it had catastrophic flaws or whatever. But the point is, it was there and it was viable. And it was the choice of physics to say, no, let's go with pull instead of push.
Throwing particles at the Moon or vice versa, the Moon at the Earth. How does he produce attraction with that? That's the mystery.
So again, how do you produce attraction? Well, you don't. Everything's repulsion. There is no attraction. Everything's a push. There are no pulls. So if two things are moving towards each other, it's because one is getting pushed into the other, or they're both being pushed into each other.
You can't do it with particles.
See, yes, you can, and it's obnoxious that after all this time he has paid so little attention. I mean, like I said, I have made an effort, and he's just so one way. He just, no matter what you say to him, he'll just tell you it's rope theory, rope theory, rope theory, you know, and he just ignores you, and it's just really obnoxious.
Newton was a particle man, okay? And Sean Carroll then uses that as an analogy for the problems quantum has as well, you know, because they have the same thing that they cannot make sense of it. And Carroll says the following. He says, to Newton, the action at a distant aspect of his extremely successful theory of gravitation was much like contemporary physicists think about quantum mechanics, and incredibly successful.
That's not how Newton thought about it. He just said it would be silly to say there's no mechanism. That would be silly, in his opinion. So there's a mechanism. He just didn't know what it was, but he thought there was a mechanism. So let's not pretend he had some dilemma like quantum mechanics has, where they're just pretending things have no location because we can't measure it. Because we can't measure their location, they don't have a location. It is that stupid. Now, Newton would have never fallen for that.
Terminology, a set of rules that fits the data to wonderful precision, like a precision.
So again, there's none of this precision stuff exists in quantum mechanics. They just keep saying that kind of crap. And of course, they're, you know, like I said, if I watch the roulette table at Las Vegas, I could write formulas dictating the probabilities, and they're going to be very precise because the probabilities are very precise. There's no magic in that. That's not making a prediction. And that's all their formulas do. Their formulas have been engineered for certain experimental circumstances. So they have a different formula for each circumstance. Like you can see the difference in the two-slit and the single-slit. They re-engineer the numbers. The variables change. And the n variable, the distance variable, they change. One's the opening of the slit, the other one's the width of the impediment. One's oddly counting where the dark spots are. The other one counts where the light spots are. You know, these are engineered formulas. Of course, they're accurate. This has been engineered to be accurate.
To do with it, right? And yet, deep down in our bones, we think it makes no sense. We can't quite make sense of it. Look at what he's saying. He says we can't make sense of it. And again, how can he make sense of it if he's trying to pull particles by throwing stones at them?
So again, let's understand, that's not what they're trying to do. So this is another huge lie, that conventional physics is a particle theory. Their particles are not solid objects. They're full of waves and amorphous. They're not in any location. How can you call it a particle theory when it doesn't have any elements that are actually particles? They just use the word because it's from the old history. Okay, it was particle physics 100 years ago, so that's what they call it. But it isn't particle physics. No part of it in any description are they particles. I mean, the only thing that might qualify as a particle is an electron because they're kind of conceding that's elemental. But they certainly didn't leave photons alone. They certainly didn't leave that being a particle.
The only force that quantum mechanics cannot...
See, the funny part is he's drawing these little dots as if they're representing photons. And it's just so funny that particle physics doesn't do that. They don't see the photon as just bits at a frequency. They see it as this stupid wavy thing. This stupid double wave. You know that, Bill. So why are you calling it a particle theory when they don't draw it as a particle? Every illustration of it is these stupid wave things, this electric and magnetic waves. So why are you saying they think photons are a particle? They obviously don't.
Is the force of pull, okay? There's no way that ever these people are ever going to explain the force of pull.
Well, there is no force of pull, so they really shouldn't even try to explain it. And even though you say you are explaining it, you're not explaining it. You're not giving us any explanation. You're saying there's this preposterous long rope between every atom in the universe and every other atom in the universe, and that something knows how to twist the ropes. Something knows how to make pull by twisting ropes. The special twisting mechanism. The super twisting energy.
So whether it's Newton's gravity or whether it's quantum mechanics, nowhere are you ever going to be able to explain the force of pull by throwing stones.
So again, the force of pull, as if we realistically see things pulled into each other. Like I feel I'm being pulled into the earth. I feel it as a pressure. I don't know how you feel it, but I feel it as being pushed. And clearly push works as an explanation. So it's just, there's no obligation to explain pull. It was very not very smart, not very clever. You don't even have to be clever. If somebody gives you the two choices and you have to somebody says I'll pay you $1 million if you successfully make one of these two things, a push or a pull, out of sticks and stones or something. Which one do you think you're going to pick for your $1 million prize? A push or a pull? Which one do you think you're going to pick? Because it's so damn easy. I mean, push is so easy, and pulls are always hidden pushes. I mean, even a rope. He's used to draw a picture of a rope around a donkey's neck. Well, obviously it's pushing on the back of the donkey's neck. It's not a pull. It's a push.
Or from Earth to the moon. And that's the entire mystery, okay? And so, you know, when quantum...
So, absolutely no mystery at all. If you're rational, you know there's two choices, push and pull. You know, push is dirt simple. And you know that, you know, when I think about it, everything I think about as a pull is really pushing things. I push on the back of doorknobs, I push. They're all pushes. All the pulls are pushes.
Deals with these discrete particles, they can't explain pull, and of course it makes no sense.
So again, they don't just deal with discrete particles, they deal with waves and waves.
You'll never be able to make any sense of it.
Waves in geometry, of course. They just vacuously say something like geometry. So they just have geometry and virtual photon. They're non-explanations. They're just empty words that don't mean anything, but there's really no mechanism.
Making sense means that you're going to give a physical interpretation for what you observed in the lab. You smash particles, you do whatever you do there, fine. Now explain it. How do you explain it? Well, you got to give a physical interpretation. That's what mathematical physics cannot do, and that's what Mr. Carroll cannot do. And
I don't think it's mathematical physics could do it. It's just that obviously they're not trying to do that. So it's a huge mistake they've made. Formalizing, like I said, the equations don't have waves in them. They have angles, and they have phases, and they have geometry. They have things that are, you know, that bullets can have, frequency. It doesn't have to be a wave. So frankly, a lot of their math is perfectly functional. What isn't functional is their understanding of what's causing the math.
And the big mystery, okay, is that you cannot produce pull with particles. So
again, he just keeps saying it. Why do I want to produce a pull? If I'm logical and I'm going to think about how the universe is dumb. The universe isn't smart, didn't go to high school, didn't go to grammar school, didn't go to kindergarten, doesn't know how to do anything. So the universe is going to figure out pull when, you know, the obvious answer is no, the universe is just going to figure out push. It's going to push shit. It's not going to pull shit.
There's only two forces in the universe, two forms of contact we can imagine. You either push or you pull.
And again, most pulls, I defy you to any pull that we engineer is a push. So go ahead, show me a pull in the real world, and I'll show you a push. There are no pulls. There are only pushes. I mean, you're taking advantage of air pressure. You're taking advantage of something. Like even when you're making a vacuum, you're taking advantage of pressure inside the vessel to push things out of the vessel.
There is no other form of contact, right? Where there is motion, forces, using Newton's second law, force, mass times acceleration. There's only...
Well, like I said, if you're logical, there's only one way it can happen, and that's push. If you're logical and rational, you'll figure out that, yeah, when you really think about it, pull is a silly notion. I'd have to imagine a magical mechanism to make a pull, realistically. There's really no way to do it. And he does it by what? Attaching a rope to some elements inside of these two atoms. And how is the rope attached? And how are the things attached to the atoms? And, is this a genuine, I mean, it's such a preposterously complex matrix. You're saying, what, so the universe creates all this rope to create something as simple as a photon? Something that moves from point A to point B at the speed of light and does nothing else? And you need all this rope to do it? It's like setting up 5 million dominoes to go from point A to point B when I could just flick the domino to point B. Why do I gotta bother with the whole row of dominoes?
You can imagine that's push and you pull. And either of those can be, you can apply Newton's equations to those two forms of...
Yeah, Newton's equations have nothing to do with push and pull. They just have to do with the effect. Okay? And again, it doesn't... Newton's equations don't say whether it's a push or a pull force. It just says it's a force. Now, it's either a force towards each other or a force away. The force has its implication, either the two bodies becoming closer or the two bodies going further away.
Those two forces, those two types of forces, okay? But you can't do that with particles. You can push with particles, but you can't pull.
Yes, you can. Just as you just stated. Again, give me an example. If I'm sucking the air out of a bottle, I'm trying to create a vacuum. What am I relying on? What am I really relying on to get the particles out of the bottle? That they have more pressure on the inside than I'm going to create on the outside. It's always push, Bill.
And so quantum mechanics is missing half the forces in the universe. Think about that. Missing.
So again, there are no, they don't exist. And if you identify a pull, I'll show you how it's a push. Except magical pulls, like I said, where you magically attach ropes to electrons or whatever. I don't know how many ropes you have. Every electron is attached to every other electron. I don't know. He usually says atoms, but I don't know whether he means the atoms have more than one rope. Well, they obviously have to have more than one rope, because they have to be attached to every other atom in the universe. I mean, just even saying it, you're saying, this is worse than flat Earth. I mean, this is... You can't do anything with it. It's like the volume of rope is an insane amount of rope.
Yeah, it make you stop and think. Okay, so Newton had troubles. He couldn't figure out how to do gravity with particles. He was a particle man. He proposed also the ether. Everybody.
So again, they could figure it out, but they couldn't figure out. They didn't have enough nuclear physics and enough kinematics, let's say, to really understand that on the nuclear level there's no friction, there's no little bits flying off, there's no heat problem, there's no this, there's no... So he couldn't understand all that. He certainly couldn't understand the full implications of inertia in this idea of these, if you do make everything a perfectly hard substance and you make some capable of absorbing, trapping energy. I mean, it's this simple. I mean, all you do, once you understand that energy is absorbed by things, and that's why it has to be released when they encounter each other. I mean, it's just so obvious that, you know, two cars coming at each other, you say, well, why can't they just cancel each other's motion? Well, that's because they're full of the force, and the force has to go through. It has to keep going this way, and the force has to keep going this way. That's the problem. So what happens is the forces have to be released, and as they're released, they end up going in all kinds of directions because they're reflecting. All the little bits are reflecting off the impact. But you're watching the energy that was trapped inside of them. You're watching it released when you watch the two things smash. It's just so, you know, I mean, it's in hindsight, I'm just saying, well, how did I spend 7 years and I didn't quite get that? But that's how obvious it is, that the energy is inside the thing that's moving. It's not, things don't just move and just keep moving. They move because they're full of the energy. It's still in them. They're possessed by it. They own it. It's in their pocket. They weren't just pushed by it. They collected it, and they hold it until they impact something, some other force, and they're obliged to release it because the matter bits can't go through the matter bits. So they have to give up their force.
They believe in the ether. And the ether was this sea of particles, invisible particles. That's what space was.
I mean, if you could make cars perfectly solid, you know, then they could bang into each other and just go in reverse. You know, no problem. But obviously going in reverse wouldn't help you any if you're trying to get somewhere. I mean, if you could jump into the other car, then you'd be going the right way, except the car would still be going backwards.
It's contained within space. Either way, they thought of them as gazillions of particles. Light went through there. Some believed it was the movement of the ether that was light. Some people still believe that. And Newton believed that light was some other particle that went through the ether. He thought about it as something separate from the ether. But again, you know, what was light? Well, he thought of it as...
Well, again, I don't know. I don't think Newton was committed to the existence of an ether. So, you know, I think Newton was uncertain. Like I said, at different periods he had accepted different theories as being viable, and for a period of 7 years or so, he thought Fadio's idea was a viable explanation.
Okay, no problem. That part he could imagine, you know, light going out because electromagnetism is some kind of push force, right? But then gravity, he was stuck there. He couldn't get past that part because...
Yeah, well, what if we had informed him? What if Newton had some way of seeing or tuning in or noticing that there was a cosmic background radiation coming from all directions? What do you think Newton would have thought then?
Okay, so if we have particles, what is the mediator of gravity? And he was thinking again, particles. He said, no, well, I can't explain with particles. Of course he can't. And quantum has the same problem. You know, they can't.
So again, it is explainable. Like every proposal, there might be some things that, you know, haven't been worked out yet. And there were 350 years ago. They hadn't worked everything out yet. But I'm just saying, I have. And Lesage, Fadio, particle gravity works. I mean, I should put my name on it too, because I didn't know Fadio or Lesage existed when I had thought of particle gravity. So, but it does work, and it's called Mach gravity, and it's a perfect explanation of gravity. If you just let it do just gravity, it works fine. The only problem is the drag issue, and as I pointed out, I have solved that problem by recognizing that the perpetual energy of photons can be utilized inside material objects to create perpetual motion. If you trap more photons going in a direction, you'll go in that direction, and you'll keep going in that direction, in spite of the drag.
With particles. Particles pulling on particles. They can. I mean, you have the gluon, right? We discussed that a couple weeks ago. Gluon is the force carrier, strong force, they claim, that keeps the quarks together. Now, how do you keep quarks together? Throwing stones at each other.
So again, that is a... You're certainly entitled to pick on physics's standard model nuances that are way exchanged, but clearly that's the kind of crap where they just made that crap up. That's theoretical crap, and yeah, it's crap. So I don't see any victory in debunking stuff they just made up.
And what they do is they put a bed spring in there. If you look up gluons holding quarks together, the pictures that you will see, officially and extra-officially, all of them.
Well, yeah, you already did this, but obviously officially and unofficially, you see it illustrated as all kinds of things, springs or bubble gum or some other rubber band type thing.
These corkscrews, these bed springs, holding the quarks together. They vibrate, they do all this stuff, but it's always a corkscrew. So people get the wrong idea that these particles are held together because they have an elongated spring there. But that spring is supposed to be a coiled, it's supposed to be the trajectory of a particle called a gluon. If you have this thing going around, you can't explain tug. And what they do is they explain it with an elastic or something similar to some kind of elastic mechanism included.
Well, yeah, I've already talked about this in the last video. This is all just bullshit. They're just trying to come up with an explanation for the strong force between electrons and protons, and this is just a nuance of that and how you break that force, and how that force seems very strong until you weaken it sufficiently.
If you try to pull the two quarks, separate them farther and farther away from each other, you need more and more strength. We all understand that. We all understand that. But you got to put a bed spring to do that, or an elastic band, or a bubble gum, or a rubber band.
It's just that you have to do it all at the same time. You can't pull an electron and a proton apart because they're going to constantly pull back. So you have to put in enough energy initially to get it all. It's like the amount of energy you have to give into the space shuttle to get it out of gravity. You have to account for the whole distance of gravity pretty much at takeoff. I mean, you have to be prepared to put in the full volume of energy, or you're not going to get off the Earth. So that's all this gluon nonsense is really about. It's not that you need more energy. It just means the further out you want to take it, the further away. If you want to get to escape velocity, you have to put enough energy in to get there. And so the further apart you want to, the further out you want to go, the more energy you have to put in. That's kind of obvious. And now they've turned that into some kind of like the energy increases as you get further apart, when it really doesn't. That's just a nuance of their poorly thought out mathematics.
That stretches. Then you can understand it. You need an elongated connector. The two particles have to be physically connected for you to apply that analogy.
Yeah, physically connected by something that's creating force, which is just silly, because then it has to be made of something that can be stretched and cause tension, and the stuff inside wants to pull together. Just end up creating a whole nother level of physics that is completely unnecessary. We have enough evidence, enough indication, I think, to know that Planck constants and the idea that stuff is in forms that are elemental. So, you can't really create mechanisms that would create a whole new physics just to analyze the mechanism. What your rope is made out of, how do your ropes twist, how do the two ropes do this, I mean, there's going to be a whole physics to just analyze your ropes. And I think a rational person can figure out that we've already kind of discerned that you can't finer grain our universe. Photons are the grain. They're the smallest grain of sand. And you're really not going to get anything less than. I mean, except for things without a frequency or less frequency. Then, yes, those things, but they're made of the same sand. There's just less sand, and it's at an inconsistent frequency. But it's still sand.
And this is the problem. The problem is that that's not what quantum says. Quantum doesn't deal with elastic bands, doesn't deal with rubber bands, with bubble gum, with bed springs. Quantum says particles. And
so again, let's just understand, no, they don't. So that's just bullshit. They clearly don't say particle. So to say they say particle, it's just wrong. They don't use them for gravity. They don't use them realistically for magnetism. And again, every time they draw anything electromagnetic, there's no particle in it.
You know, is supposed to go outwards. So the analogy doesn't follow. And so that analogy is force-fitted in there. It doesn't belong in there. But they try to get away with it. Okay, so
the gluon doesn't belong there, and the quark and all that crap, and any interactions between quarks and gluons, none of this stuff, none of these things even exist for more than a trillionth of a second. So none of these things are elemental particles. None of them are the real movers and shakers inside of atoms. It's all just kind of bullshit. The real mover and shaker is the proton and the electron. They're the plus and minus, and the force is equally segregated, identifiable as plus and minus, and that's the ball game. You don't need to make any other more complex elements. That's all you need to answer all the questions. Protons, electrons, and photons. You don't need anything else.
Carroll continues, and he says, okay, so Newton couldn't figure it out. Let's see if someone else did. And he says, yeah, someone did, and his name was Laplace, a French guy, okay? And Laplace says, Sean Carroll says the following for Laplace. Says, Laplace came up with a new theory of gravity that gets rid of action at a distance. Oh my God, that's great. That's all we want.
It doesn't get rid of it. It's again, it doesn't explain cause. It just explains it. It just qualifies the effect. It's just an illustration of the inverse square law, for fuck's sake. It's another diagram of the inverse square law, which Newton already discovered. It has no value as a cause. It doesn't explain how it works. It just explains, it explains what happens. It doesn't explain how it happens.
Okay, we wanted to figure this out. And so what Laplace says is that instead of thinking about random forces between objects very, very far away, imagine there's a field filling the universe. So there we have your field, okay? And what that means mathematically is that at every... Listen to this, okay? This is the important part.
Yeah, no, there's no important part here. Obviously, the field has to be created by the existence of the matter, so it's no different than just saying bent geometry. It's no different than creating some artificial mechanism that somehow knows there's supposed to be a field around the matter. It's not making the field out of something. It's not a cause. It's just, again, another way of illustrating the effect.
Mathematically, he's telling you what a field is that at every point in space there's a number of value of the field. Just like the temperature of the air in this room.
Right, and the same, there would exactly be this number, this intensity, if you made it out of particles. Random particles banging just flying through the universe will create that scenario for every material object. And if you bring two objects together, those numbers will appropriately change between the two objects, and you'll end up with a bunch of stronger force between them. So it works perfectly. Mach gravity does that.
Point, there's a value, the temperature at that point of the air. Okay, so there you have what a field is. We have a field, and that's a bunch of numbers, a bunch of value. That's all a field is. Just that.
So again, their field isn't a field of something. They're just describing it as an effect. So again, you're implying they're calling this a cause. They can't call it a cause. They're calling it an effect. They're describing what the facts are. They're not bothering explaining how that fact is created.
Okay, numbers, magnitudes, and so according to Mr. Carroll, he says that Laplace figured out the problem. He solved the problem by saying, we have the concept of field. I don't think he called it a field at the time. No, he didn't. In fact, the field comes from Faraday, which comes sometime later. But Laplace thought in terms of this field of something extending throughout the universe, okay? And
again, and no mechanism for why there's a 9 in the middle, and why there's an 8, and why there's a 7, and why there's a 6, and why there's a 5, and why there's a 4. No mechanism. It's no different than bent space. It doesn't tell you anything about how that field is created.
Mr. Carroll says that this notion that Mr. Laplace came up with is the notion that they have a field. In other words, values at each point in space. As you can see, the way I illustrated this is the big numbers are in the center, and as you get farther and farther away from the center of something, the force gets weaker. Whether you're talking about electric or magnetic, or whether you're talking about gravitational force, it gets weaker the farther away you get from the particle or the thing in the center, whatever that is. And how far does the field reach? According to mathematical physics, it reaches to the very edge of the universe, of space-time. Okay.
Right. Well, that's because theirs is just a mathematical theory, so obviously they're not recognizing one of the fundamental truths, which is this force is radial. And the reason why it's 8 close and it's only 2 further away is the radial force is diverging with distance in 2 dimensions. It's going further away this way and further away this way. That's the inverse square law. Further away this way, further away this way. That's the cube. So the cube gets bigger and bigger and bigger with distance. So theoretically, at the end of the universe, there would be whole hunks of space that may never see a ray of light, because the rays have diverged so much from an object that they will miss that piece of space entirely. So to say it's infinite is to imply you would need an infinite plane to catch it with. If you have an infinite net somewhere at the end of the universe, well then yes, you'll catch all the light. But if you stick this pen at the end of the universe, it may never get hit by a ray of light from our sun. Ever.
So, just in case you're wondering, this field does cover the entire universe. But it turns out that every particle has a field, and all these particles or all these fields are superimposed one upon the other.
Right. It's no different. It's just like saying, look, Einstein's saying everything bends space. Now, what he didn't say is whether photons actually do, but frankly, everything else bends space. Everything creates a dimple around it, and this is just a description of the dimple. It's absolutely no different than Einstein's curvature. So again, it just points out how weak Einstein's theory is, that this would already, you could already create lots of mechanisms. Like I say, I think Newton could have figured out that gravity is just a bowl. And I just think he knew, I can't just go to people and say, the bowl did it. It's the universe is bowling. I think he knows that everybody would have said, that's not an answer. Yeah, everybody can draw a picture of the inverse square law. So what? That doesn't explain how. How does the universe bend like a bowl?
To figure out, how complex Mother Nature runs her, how complex Mother Nature's universe is.
So again, it's really simple, and it's the only thing that made it complex is when you start making left turns when you should have made right turns. You mislabel things. You go pull instead of push, quite obviously. You go pressure rather than wave.
Field. Every particle in the universe has a field. A muon has a field. A pion has a field. A neutrino has a field. An electron has a field. All these have protons. Every quarks, every particle you can think of that you can imagine has a field. And that's not counting, the gravitational field, like from, the...
It is counting the gravitational field. It's completely... that's exactly what he's explaining, is the gravitational field.
Or whatever. So we've got all these fields all over the place. And it makes you stop and think, what a complex world the mathematicians have created.
Yes, it's a terrible shame they've gotten so much wrong. And again, the funny part is that magnetism is the same field. It's essentially gravity just being segregated, and therefore the same energy that went in as gravity is the very same energy that comes out as magnetism. It's perfectly conservative. So if you make the energy of gravity into real energy, then you can explain where the energy for a magnet comes from. Because by segregating the force, it creates the ability to have polarization and to create a dipole and to have attraction and repulsion in the right orientations. And so it explains it all. It explains why magnets look like they're producing energy when they're not. They're just converting energy that was coming into them anyway. Just like gravity, energy that was going into a body anyway.
We're in a world in which these people say that every particle has a field. All these fields are superimposed upon each other. This is how the physical interpretation they're giving for how the universe runs. Now, does this make sense to you? Doesn't to me, but...
Yeah, well, what doesn't make sense to me is your theory. Your replacement is worse than their nonsense. And the simpler answer, the Occam's razor answer, is to recognize all the little bits that are confusing us. The photon, the gravity, the magnetism, they're all moving the same speed. Which is just a huge giveaway that they're all the same damn thing.
You have all kinds of people out there. Okay, so Mr. Carroll continues. He clarifies. He gives us the notion of Laplace's field. Okay, and he says the following. He says, there isn't anything acting instantaneously and spookily at a distance. The gravitational potential is very low here near the Earth. And
Alright, well, we already know that there's no instantaneous, okay? We know that gravity's not instantaneous, okay? So that was a problem Newton had, because they couldn't know all this stuff. But we do. We know light's not instantaneous, we know gravity's not instantaneous, and magnets aren't instantaneous. They are moving at the speed of light. The force effect has to travel the distance, and it has to travel it at a speed. The speed of light. The speed of force. Damn it.
as you go to the moon. And that change keeps going forever. Again, forever means that it reaches all the way to the edge of the universe.
And again, yes, theoretically it can, but again, there's no obligation for it to ever hit one single location. It's just a generalization that the photons keep going. The energy keeps going. So any effect you've had on them, that if you've trapped some, if you've kept some photons from going where they would have gone, the effect of them not getting there will be felt by something a trillion zillion light years away. If I'm blocking a force that was heading right for it, obviously that force won't hit it. So, yes, in that you can just say theoretically that has to be true. Not surprising.
The universe has an edge. Okay? So the Earth is affecting something that stretches throughout the entire universe, the gravitational potential field. There's nothing acting across a very large distance. Well, there's a bit of a contradiction there, you know, because...
See, they're just ignoring the obligation to do cause. So if they just make it a field, they just say, we'll just concede the existence of the effect, and we won't bother talking about causes. We'll just talk about effects. So that's all he's saying here, is that we'll create a fake field that automatically initializes by rules we say. So the field gets changed depending on what matter bits we put where, automatically change the field numbers. They're not dealing with what causes those field numbers to change, which is a huge cop-out. So you legitimately can gripe about the fact that they're just saying, let's analyze effects and never even have a conversation ever again about a cause. It's just effects physics, which is the easy physics. It's just so fucking easy to sit there and figure out what something's doing when you can watch it do it. Again, writing the formula for how often dogs poo doesn't deserve a Nobel Prize.
And he's saying that there is a field, And then he qualifies it as nothing. He says there's nothing acting across a very large distance. Well, what is this field thing? I thought the field extends throughout long distances and all the way to the edge of the universe.
Well, he's not even reading what the guy wrote, so let's see what he said. The gravitational potential is very low here near the Earth, and it climbs upwards as you go towards the moon. And that change keeps going forever. So the Earth is affecting something that stretches throughout the entire universe, the gravitational potential field. There is nothing acting across very large distances. So again, I think it's just silly. We know that it takes time for the effect to travel, so it's stupid for him to say there's nothing acting across long distances, because if it was nothing, it wouldn't take time for it to get there. So that is stupid.
Nothing? So he's got a contradiction in the way he's presenting this. He's saying on the one hand, you have fields. Each field extends to the edge of the universe. And
yes, and we know that it extends there, but it takes a long time for it to get there. Again, we're not feeling if a star 2 billion light years away blows up, we don't feel the absence of its gravitational field for 2 billion years. We still think it's there. We're still being pulled towards it, even though it's gone. Because the force that's going to now go through that hole that's now been created, that empty, so there's not something blocking force anymore. It's going to take 2 billion years for that force that now can get to us to actually get to us. Because it's moving exactly the same speed as light. Because it's the same damn force.
There is no action at a distance. So what is this field thing? I thought the field was put in there, well, that's what was being proposed, to mediate action at a distance. And again, he's saying that Laplace and also, I guess, quantum mechanics.
Well, again, I don't think Sean Carroll is stupid enough to think that action at a distance in the sense of the instantaneous action is the same as the action at a distance of a force effect. But again, he's not accepting he's not bothering to deal with the force. He's just going to deal with the implications of the force. So again, he's just doing what does it do math, not how does it do it.
General relativity are saying, look, there is no action at a distance, but there's a field that extends all the way to the edge of the universe. And how does the field do it? And again, what they're trying to tell you here is that they're going to do it mathematically. They're just saying that there are values, there are magnitudes, there are numbers stretching from from an atom or whatever particle, all the way to the edge of the universe. So all they can do is have values.
There are, as a practical fact, that is true. So I'm just saying, you can't deny that that's the implication of whatever cause you come up with. Whatever cause you come up with, that's the implication it has to be accurate to in the end, is there will be a number of force elements, there'll be things that will impact you or not impact you depending on what's around you. So that's just the truth of it. If I'm in the forest and the sun has to go through the trees, I know their pattern of light is not going to be consistent.
On this region, and all they can do is measure and say, well, the value of the field could be magnetic field, it could be a gravitational field. The value of the field over here is such and such. But that doesn't tell me what the mechanism is. How does that field affect this thing that is so far away?
Right. Well, I'm just saying that's the critique. They're still just doing cause. I mean, they're still just doing effect. So Einstein 100 years ago made it popular to say, screw causes, I'll just give you effects. I'll give you a silly little diagram of the inverse square law, and we'll call that physics. And yeah, it's rubbish.
Issue I just pointed out with the black hole. The black hole has mass, okay? And they say it's got so much mass, runaway mass, that it can affect a star far away. Fine. That's a description. You can say, look, if you get close to the black hole, you're going to feel more mass. You're going to feel more gravity. If you get far away, you get less gravity. Okay, fine.
I know, but this whole thing had the black hole has to do with also what kind of black hole, right? Because you have these little micro black holes and then the supermassive black holes. So obviously the small black holes have no reach that would be more than like our moon or something. They're just saying that there's as much mass as the moon in a pea somewhere. So they're just, bullshit.
What's the mechanism? And that's what they're skipping. They're never going to tell you the mechanism because a mathematician only does numbers.
Well, no, like I said, it's not the math's fault. It's worse than that, okay? The math could acknowledge properly what something's made out of. And, the math wouldn't change much, except you would just change something like frequency might be period instead. You might use some wavelength would be period. You'd use some other variable more rational to the argument, the truth of it. You wouldn't worry about wavelength between bullets. You'd recognize it's a period between the bullets.
He does equations, he does values, he does fields. He can't tell you a mechanism. He can't tell you how the magician did the trick. He only tells you what the magician did on stage. That's
right. He gives you a formula. The magician, lambda, which will be if there's a hat on the table, okay, if lambda, hat on the table, rabbit, okay, if magician pulls on sleeve, delta thigh, pigeon. Yeah, that's all they're doing. They're just describing the effects. They're not dealing with causes. And that's what physics is supposed to be, in my opinion, is causes. The effects, we can see the frickin' effects. Again, they just keep talking about their stupid math. 90% of their math, nobody ever does, because no one could give a crap. It's useless formalizations. Nobody cares how many meters apart the stupid bars are on the double slit pattern. No one gives a shit.
So he goes on, he clarifies a little more what a field is. That's Mr. Carroll here. He says, that's what we do these days. We talk about particles and about fields. In one sense.
So again, yes, this putz talking about, we talk about particles. We talk both about particles and about fields. For them to use the word particles is a lie, because their physics doesn't have any except for an electron. It's just made out of gooey mush.
Particle and the field are the opposite of each other. Okay? A particle is something that has one location. Here's a particle, it's nowhere else. A field is the opposite of that. A field is everywhere.
So again, more nonsense, because obviously, yes, their field is a consequence of the existence of the particles. Things with mass. Things without mass can't be affecting the field, can't be creating a field, can't be moving those numbers around.
Point in space, there's a value of the field. Again, he clarifies that a field is just a bunch of numbers.
And those numbers are the amount of photons. So obviously, if there's an external light being shined on you, external lights, the light's shining in all directions, the truth is a certain number of photons are just heading right for you. And as they get closer and closer, they get closer and closer together. As they come in, converging on you, they're getting closer and closer together, making those numbers bigger and bigger, just as if it was going out and getting bigger and bigger. It's so obvious. These are rays of force.
There's going to be an excitation, a vibration of those numbers. Because that's what they're saying a particle is. A particle is the excitation of a field. And then he tells you that...
Well, again, he's saying that's the consequence of a particle. I don't think he's saying that's what the particle is. That's like saying the Earth is the excitation of a field. Well, I think they concede the Earth is a little bit more than that. The Earth is a little bit more than the gravity it's creating.
A bunch of values. So we're introducing physics in the context of mathematics. Okay? We're saying on the one hand that...
Well, again, mathematics isn't the problem. And formalizing what you see is a perfectly rational thing to do. That's what the word formula means. Formalizing. You're taking the essence of it and making a nice, concise diagram of the essence of it. But it doesn't have anything to do with cause. I'm described quite completely as what I am. Now, if you want to go a step further, you can make a formalization of what I am. But what would be quite irrelevant to that formalization would be who my parents were. See, that's what the physicist should want to know, is what caused me to be this configuration. Describing what configuration I am can be formalized, but the more important thing is understanding the chain of events that caused me to be this.
A particle is a field, a vibration of a field, and a field is just a bunch of numbers. So we're mixing physics with mathematics here.
Yes, well, it's really, the mathematics is the inverse square law, and it's a real thing. So that's perfectly rational to say, what's the implications of the inverse square law? How do we formalize the inverse square law? So all this is sort of legitimate. Like I said, even thinking in terms of Einstein's convergence is perfectly rational in a sense, as long as you understand that's just a way of thinking about it, because what it really is it really, I said convergence, right? When Einstein's, they don't ever want to say that word because, because then it implies something converging, the external player. And again, they're stuck with that analogy. When they teach the subject, they end up basically describing water pressure moving towards the earth.
Right, they don't match. Because if a field is a bunch of numbers, you can't say, well, a particle is a vibration of a field. You can't use that terminology.
Yes, it is nonsense. But clearly, all the particles affect the field. So if the particle moves, what happens to everything around it? It's if I'm sitting here with a tree in front of me and the sun, and the tree moves, well, all of a sudden now the sun hits me. There's implications to movement. But no, I'm not thinking the sun's pulling on me. I'm not thinking the sun, the photons are pulling me towards the sun. They're negatons or something. They're clearly particles. And I either get hit by them or I don't get hit by them, depending on whether there's a tree in the fucking way.
Talking about physics, you're talking about a physical object. You're saying this physical object is really a vibration of numbers. And the issue really is that they don't have particles.
Yeah, it's exactly what it is. Like I said, if you were thinking about it, just measuring shadows on a piece of paper and you moved an object around, the shadow moves with the object. Clearly it affects the field. Movement will change the pattern.
Quantum mechanics. What they're trying to say to you is that they don't deal with objects. There is no such thing as a particle. What they call particle is just a concentration of values. It's where the field becomes stronger. The numbers are greater. That's all it is. And when you get farther away from the center of the...
Yes, they're accurately describing the inverse square law. So again, yes. It's good to make it nice and technical, figure out exactly the inverse square law. But yes, it is a very simple thing. So yes, it's r squared. It's not that complicated. 1 over r squared. Gee, yes, everybody can figure that out. Not too complicated. Half the distance, twice the size. 4 times the size difference. I go this 4 times bigger here. See? 4 times bigger. There. Okay. We got that. Not complicated.
Particle, whatever a particle is, then the values get weaker. That's all they're saying. It's like climbing a mountain and coming down the mountain.
Yes, they're saying nothing. They're just playing like they're pretending because we will draw it differently that we're somehow drawing something new. They're drawing nothing new. They're just drawing it differently. And they're saying, look what we did. We made it different. We didn't use bent space, we used bent numbers. I mean, it's just bullshit, yes. But don't pretend they're the people you should be arguing with. They're idiots. Try me, because you'll lose.
The valley, right? When you're at the top of the mountain, at the peak, that's the particle. And when you come down the mountain, well, They're getting away. We don't know where the particle is chopped off because values continue eternally. Okay, and so the question is, where does the particle begin? What's the perimeter of the particle? Where does it begin? Where does it end? Well, it ends at the peak, I guess. No problem there. But where does it begin? If we're starting at the base of the mountain, where does it begin? Because it continues forever. And so again, they're using physics in the context of math, and it doesn't really match.
Well, whatever. More nonsense. But anyway, the easy explanation, as I've put it, is that math has to be understood as just a formulation of effects. Math doesn't do causes. It just does what happens. It doesn't do how it happened.
There's no correlation. Physics, you can say, look, this is a rock. But you cannot say rock is a vibration of a bunch of numbers. Vibration of a field.
Yes, you can. If you put the rock up to the sun, you'll see how the rock can vibrate the light that hits your eye. No problem. I guess this is getting redundant, so we'll call it a day. Yeah. So anyway, there's nothing to say. I mean, this is, their theory is bad. His replacement is worse. My answer fixes it all. It's the right answer. I have the right answer. It just turns out that way. I happen to have the right answer. And if you're a reasonable, sensible person, you'll figure that out. All the forces move the same speed. Jeez. They act just like each other. Why do they think they called magnetism virtual photons? They called them that because, damn, it sure does seem like it's photons. Damn it.